But it is 6 o'clock. So I'm going to send the attendance link in like 1 more second because I see one person is joining. 2 people are joining, but yes, yeah, I totally feel that. Here is the attendance link, and please sign in just your KSU ID and the date. And before we get started, is there any questions? Or is there anything that you want me to briefly cover? I don't know how many of you guys have read the chapters yet, or have looked at the exam. Is there any, if you have, is there anything particular on the exam or in the sections that you want me to like address or talk about real quick before we get started on the practice exam? I see a couple more people are joining. What are the intervals for trig functions? And when you say intervals, do you mean like when you're solving for like a definite integral, like the a and b? Is that what you're talking about? Oh, okay. I'm not sure. I know that the arctangent is negative pi over 2 to pi over 2. But honestly, that's, I don't want to say that's the only one that's important, but that's the only domain of any of the inverse trig functions that I personally know. And if you're going on to Calc 2, that's something that you'll need to remember, especially when you get towards the ends of integrals / series. But honestly, I don't know the domain for the other ones. You could probably Google it. Is it on the practice exam? Like not in the memorization, on the, like when you take the antiderivative of the inverse tangent. Yeah, problem 12.7. Yeah. But the thing is, he won't give you, he's not going to give you like an invalid domain because like you don't know how to deal with that. Like if there's a hole in the graph, like where with the domain that he gave you, you wouldn't be able to deal with that in an integral yet. You don't learn how to deal with that till like end of Calc 2 when you learn about improper integrals. So that's not something you need to worry about. But I think, well, other than that, you really, it should just be literally exactly what you've been doing, but you're going to plug in those numbers and then subtract the two functions from each other with the different numbers. Like that's what you're doing with a definite integral. I think a few more people have joined, so I want to send my attendance link one more time. Just please sign in with your KSU ID and the dates. But that being said, I guess we can go ahead and get into the problem. Let's start with, I am going to start with 12.1. It shouldn't take long, but just so I can go over it with you all. It's kind of related to 12.2. So in 12.1, they want us to rewrite this Riemann sum as an integral, right? So they want us to rewrite this Riemann sum, which we know can be rewritten as an integral. And this one hopefully isn't too hard for y'all. Simply because a lot of it's just recognizing where the similarities lie. And I'm going to point that out for you guys. C sub k minus C sub k cubed delta x sub k, and this is on the interval 2 to 7. Alright, so I guess before we start this, there's this really good illustration of what the different parts of the integral are. And we're basically just going to assign these different all these different parts to a portion of this Riemann sum to rewrite it. So if we have like a generic integral, right? The integral from a to b of f of x dx, f of x being our function, we can say, okay, this is our f of x, so we know our f of x is going to be this right here, right? And also everywhere we see a ck, c sub k, that's going to be equal to an x, right? So right here, where we see the c sub k, in our function, we're going to replace that with x. We also know that this interval is very similar, or is in the form of the interval from a to b, which if you notice, we have an a and a b right there. So we know our a is going to be equal to 2, and our b is going to be equal to 7. We also know we see this delta x sub k is going to be replaced with our dx. And then our integral sign right here. I guess I should use a different color. This integral sign right here is going to be replaced with this summation thing. Am I forgetting anything? I think that's it. I guess we should also write down what our f of x is equal, right? Our f of x will be equal to the arc sign, or sine to the negative 1, however you want to write it, 1 over x minus x cubed. And now we just put all this together to write in an integral, right? To transform this Riemann sum to an integral. So it's going to be the integral from 7 to 2, because those are our a and our b. And then our f of x is the arc sine of 1 over x minus x cubed dx. Does that make sense? It's just rearranging these parts. I mean, this is going to be the same every time. This is going to be the same every time. Your f of x is just going to be whatever inside those brackets. And then your a and b is going to be whatever's in there. Yeah, so it really, yeah, the integral does look so much nicer than the Riemann sum, I agree. But this is the general process, and I think my note sheet might illustrate it a little nicer, but this is the general idea of it. And even if you feel lost on the exam, even if you give something really complicated right there, I would really just suggest you go through this whole process. Because it'll make it a little easier. Yeah, that's the answer. This is the answer right here. The solution. The only part of the question is just to rewrite this right here as an integral. Because a Riemann, like an integral by definition, is a Riemann sum. Yes, actually, that's 12.2. 12.2 is solving a Riemann sum, where he gives you an integral that's a really simple integral, and he asks you to solve it using Riemann sum. And that's what we're going to do in this next question, which is, in my opinion, probably the hardest conceptualized on the exam, because it's something that is kind of new to you guys. It's kind of similar, you know, that summation problem that was on the last exam. It's going to be like that, but harder, with a little more to it. Yeah, but I promise it's not that bad. It's just kind of algebraically intensive, and hopefully it won't be too confusing. I think one more person's joined, so that's the attendance link for whoever that was. Was there any questions on this one before we move to 12.2? Because we're going to go in the reverse order. Awesome. All right, so for 12.2, they want us to evaluate exactly this integral, the integral from 1 to 2 x squared dx. And we're going to evaluate that using the limits of a Riemann sum. So we're not actually using our integration, right? You can use this, you can integrate this to check your answer, and honestly, I would highly suggest you do that at the end if you have time, just to make sure that you didn't make a mistake somewhere. And even then, still go back through your work and make sure you didn't make a mistake anywhere, because you can make a mistake inside the problem and still get the right answer. That's actually exactly what I did on this problem. Because this problem is in his Calc 2 class, one of the first exams. That's exactly what I did on that problem in Calc 2. So you have to be really thorough with your algebra, make sure you wrap everything in parentheses, because it's really easy to get lost, or it's easy to not multiply something because you miss your parentheses, and that's what I did. So please just be very thorough, because I would hate for one of you guys to get a mistake like that on this, even if you got the right answer. But hopefully I can break this down for you. On the exam, he gives you this formula. At least I remember. Let me double check. I'm pretty sure it's on the exam. Yeah, it is. On the exam, he gives you this formula. So you don't have to memorize this or anything, but he gives it to you. And it's this integral from a to b, f of x dx is equal to the limit, as n goes to infinity, of b minus a over n times the summation, I'm going to have to zoom out for this, of k equals 1 to n of f of a plus k over n times b minus a. And I know this looks really complicated. Let me look at the one on the memorization sheet. The one on the memorization sheet is, it has to do, it's a little more complicated. So this is not the same that's on the memorization. It's a little different. If you notice, if you look at the one on the memorization sheet, it's the limit as, I think it's the norm of p goes to 0, and it's the f of ck times delta xk. And it has to do with what that limit is evaluating, why what's inside is different. But they should be equal to each other. It's just you're using different, we're evaluating a different limit, if that makes sense. Like, this limit is different. The limit as n goes to infinity is different than the limit as p goes to 0. Like, they're probably equal to the same thing, like, when you evaluate it that way, but it's different notationally wise, and I think technically the other one is a little more complicated to solve than this one. But this one is specifically given on the exam. The other one is not as complex as this one. It's just the same limits with something different down here, and instead of all this mess in here, it's just the summation, this part of f, and then there's a ck in there, and then there's delta xk. Oh, I didn't even see that email. Thank you, Evelyn. Okay, that's good. I didn't see that in the email. I must have glossed over that. So thank you. And then I forgot the delta x to the k on the back. But all we're doing, yeah, I guess I'll double check after and send a message in the GroupMe. Just to make sure. I would still know the one on the memorization just in case, but he's giving it to us? Okay. Alright. Well, the first thing that, when in this problem, the first thing I would do is you want to just simplify this. Because we're going to work with this portion right here, but it looks like a giant mess. So if you notice, we're given this integral, and we're given it a definite integral, right? So this is equal to our integral a to b f of x dx. So we know our a is equal to 1, and then our b is equal to 2, right? So we're going to plug in our a and our b. So we're going to plug in plug into the summation to simplify it. And wherever we see a b and an a, we're going to plug in those values. Right. And then we're going to replace this integral right here with the one that we're given. Right. So we have the integral from 1 to 2 x squared dx is going to equal this limit as n goes to infinity, b minus a. B is 2 and a is 1, so it's going to be 2 minus 1 over n times the summation, k equals 1 to n, and then it's f parentheses. This, I will say, this part right here is just the same function, your function f of x is equal to x squared, evaluated at that inside portion. So keep that in mind. So we're going to plug in a, our a is 1, plus k over n times b minus a, which is going to be 2 minus 1, delta xk. All right. And then I'm just going to keep writing equals so I don't have to rewrite that integral. And then we're just going to simplify this. It's going to be a limit as n goes to infinity of 1 over n times the summation, k equals 1 to n, f of 1 plus k over n, delta xk. All right. Where is the square? What do you mean? Oh, well, we haven't substituted for our f of x yet. So our f of x is equal to x squared. And so we are going to have to substitute this f of 1 plus k over n into that x squared, right? So if we substitute that for x, we would get 1 plus k over n squared, right? So from here, we're going to substitute for f of 1 plus k over n. I'm going to substitute this part. Does that make sense? Whatever this part is simplified in here, we're going to end up substituting it in for x. All right, so doing that, we see that it's going to be the limit as n goes to infinity of 1 over n. We have the summation of k equals 1 to n, and then our f of 1 plus k over n is going to be 1 plus k over n squared. And now we're just going to multiply 1 plus k over n by itself and simplify. So we still have that 1 over n. And so multiplying it by itself, we get 1 plus k over n plus k over n plus k squared over n squared, delta k, or delta xk. And now we're going to simplify. A lot of this problem is just simplifying and doing some algebra. We're going to have this 1 over n. We're going to have our same summation. And we're going to get 1. K over n plus k over n is 2k over n. And then plus k squared over n squared, delta xk. Now, for those of you that were at that one SI session where I had additional practice problems for summations, what do you know whenever you have a summation wrapped in these parentheses, right? What can you do with the summation? See, the summation is applying to all those everything in that parentheses. Yeah, we can distribute it. And if you notice, we have a 1 right here, a k right there, and a k squared. And if you remember, we were given those values for what to substitute in. So our goal from this point onward is we're going to substitute or distribute that summation, and then we're going to try and make that summation look exactly like our formula, just like we did on the last exam. Right, so we're going to distribute that summation. So we have 1 over n times the summation k equals 1 to n of 1. I wonder, let me look at, I wonder if he keeps the delta x sub k. Sorry, I'm just looking at it because I didn't keep it on mine. Actually, on his, he doesn't even have this delta x sub k. So my bad, we don't actually have to have that. I don't know why it's not on here, but on the other one, but we don't need that there. But we distribute it to the 1, and then we also distribute the same summation sign to the 2k over n. And don't forget that 1 over n right here, let me use pink, this 1 over n is going to apply to all of these, all of the summations, right? Don't forget, because we're distributing this whole thing to each. Right, so it's going to be 1 over n times the summation of 2k over n plus 1 over n times the summation of k equals 1 to n of k squared over n. Now, like I said before, we're trying to get the inside to look exactly like our formulas, right? So what do we need to pull out of our second and our third summation in order to make it look like that? Because our first one already looks good. It's just the summation of 1. We don't have to pull out anything. But what about for this one in the middle and this one on the right? It should be an n squared on the bottom. Yeah, so it's 2 over n for the middle. Yeah, that's absolutely right. And then what about for the last one? Yeah, just the 1 over n squared. This is exactly right. So I'm just going to rewrite this one more time. We're going to pull out that 2 over n, so we're going to get 2 over n squared outside that second summation. Delta x is b over a minus n, isn't it? I think so. I think that's why, because that's not in the memorization part. That makes sense. Yeah, that makes sense, yeah. They probably explain it in the chapter. It's just been a while. Because this is really the only time. It's really good to do this so you understand what the integral is actually doing. Because this is a lot closer to the actual, like, what an integral is actually doing when you're evaluating it. Makes you appreciate integrals a lot more. Here, we're pulling out the n squared, so we're going to have that n cubed on the outside and k squared on the inside. So if you notice, all those summations in the parentheses are exactly formulas that we already have memorized, right? Just as a reminder, the summation of 1 is equal to n. The summation of k is equal to n times n plus 1 over 6. And the summation of k squared is n times n plus 1 times 2n plus 1 over 6. Right. Oh, it's over 2. I don't know why I wrote 6. I promise I knew it was over 2. I was just thinking about the third one. Thank you, Nathan. Yeah, so these are our formulas. And all we're doing is, last time we had a value of n, right? Up here, use a different one. We had a value of n up here to sublimate, but this time we don't have that. So we're literally just substituting in this formula and then simplifying. Right. I'm actually going to leave it right here for this step because I think the next step is what I do to substitute it in. I'm going to substitute in these formulas, and that's going to be our step 2. My bad, is to substitute in formulas. And also at this point, I recommend, this is just personal preference, so you don't have to keep writing that limit sign. What you can do is you can set your integral from 1 to 2 x squared dx equal to the limit as n goes to infinity of s sub n, which just means like the sum, and then we're evaluating n, and then it's just equal to that same limit that we have up there of this 1 over n summation k equals 1 to n. And if at any point there's a question, please stop me and let me know, because I want to make sure that you understand this. And then plus 1 over n squared summation k equals 1 to n k squared. I do this because then you can just set s sub n equal to that summation. And this is optional. I think for me it just helps realize what I'm doing. I'm not taking the limit yet. I'm solving for these. I'm substituting in these formulas and simplifying as much as possible. And then you take the limit. Plus 2n squared over that same summation. Okay, and then 1 over n cubed. K equals 1 to n k squared. And then from here we can just substitute in these formulas. Does it make sense why I'm doing this? It's just so you don't have to always write that limit, because I think it's kind of annoying, especially when you're simplifying so much, which you're going to be simplifying a lot in this step, is the only reason why. So let's substitute in those formulas from up there. So for that summation of 1, I'm going to substitute in n. And then times our 2 over n squared, we're going to substitute in our n, and plus 1 over 2. And then we're going to substitute in we still have our n cubed, and that's going to be multiplied by n plus 1, 2n plus 1 over 6. All right, any questions from this step? Because from here, we're just going to be doing a lot of simplifying. All right. You see this n on the bottom crosses out with that n up top in that first term. In the second term, we see that one of these n's is going to cancel out with that n up top. And that n on the bottom is going to become a 2 because it cancels out with one of those n's up top. Right? So let's rewrite this. We know that first term, n divided by n, is just going to be 1. Plus, now we're going to have also these 2's cancel out. So now we're left with n plus 1 divided by n. And then we also have plus, we're going to have our n plus 1 times 2n plus 1 over 6n squared. So now in this next step, we're going to divide up this middle fraction. We're going to make it n divided by n plus 1 over n. right? Because if we have one term on the bottom, we're allowed to separate the top fraction. So we're going to have s of n equals 1 plus n over n. We know n over n is just going to be 1 plus 1 over n. I'll keep those brackets there just so you know that's where it came from. Plus, and then we're going to multiply that top part out. N times 2n is going to be 2n squared. 1 times n is n. 1 times 2n is 2n. 1 times 1 is 1. So all going to be over 6n squared. 1 plus 1 is going to be 2. And then we still have that 1 over n. And then simplifying that top part, we get 2n squared plus 3n plus 1 over 6n squared. And now again, we're going to separate this middle part into 3 different fractions. So we have 2 plus 1 over n plus 2n squared over 6n squared plus 3n over 6n squared plus 1 over 6n squared. Probably should have chosen a different color for doing that, since I just did the green right there. Let's do orange. What happened to the n? Are you talking about from right here to right here? I added that n and that 2n together. N plus 2n is 3n. Yeah, that's all that happens. And then I just separated the fraction. And then from here, we have that 2 divided by 6, that's going to be 1/3, and also those n squareds cancel out. So we have plus 1/3 plus n divided by n squared is going to be an n on the denominator. 3 divided by 6 is 1/2. So we have 1 over 2n, and then plus 1 over 6n squared. I guess I'll keep this for one more. And then now we're going to add everything together. We see that we can add this 2 and that 1/3 together. We can add this 1 over n and 1 over 2n together. So for up here, in this step where the n plus 1 divided by n, when we have one thing on top divided by one thing on the bottom, we can separate it into n plus 1 over n, and then the 2 n's cancel out just to be 1 plus 1 over n. Yeah, no, that's happened with Wii before, trust me, where it doesn't click, and then like you see it's done with something else and you totally get it. It's just like that sometimes. Where was I? Oh yes, we have to add the 2 and the 1/3 together, and that 1 over n plus 1 over 2n. So to add that 1 over n plus 1 over 2n together, we can just multiply it by 2 over 2, right? Find common denominator. And then for this 2, we need a denominator of 3, so we just multiply it by 3 over 3. So we're going to get 6 over 3. And then I'm going to add that 1/3 right there, because we're going to add those together. Plus, and then we have our 2 over 2n plus 1 over 2n. And then we have our 1 over 6n squared. And this should be our last time simplifying. We get 7/3 plus 3 over 2n plus 1 over 6n squared. So So this is our S of n. It's not our final answer, but this is our limit completely simplified, right? And I think now you guys every time. Yeah, that's the whole reason why. And you are allowed to do this. All right. And our step 3. Is there any questions before I move on to step 3? Yes, it's a lot, but it's gonna be the same process every time. And it takes a really long time as well, just algebraically. Our step 3 is just to plug our S of n back into our limit and then solve the limit, right? Plug back into limit. All right, so we have our integral from 1 to 2, x squared dx. It's going to be equal to the limit as n goes to infinity of S of n, and I'll just rewrite it again. Integral 1 to 2, x squared dx equal to the limit n goes to infinity of 7/3 plus 3 over 2n plus 1 over 6n squared. Now, since we've simplified all the way, we don't have to think about, oh my gosh, how do I evaluate this limit? Because it should be ready to evaluate once you've simplified completely. Oh, I don't need to write that limit again. So plugging in infinity, we're going to get 7/3 plus 3 divided by 2 times infinity plus 1 divided by 6 times infinity squared. So what happens to these two what happens when we divide a constant by an infinitely big number? Yeah, exactly. They're going to go to 0. Right? So this integral, and this is going to be our final answer, is equal to 7/3. This is the solution. And there's an optional step 4 where you check yourself by actually doing this integral. So like step 4 is optional. And it's just to integrate that integral, right? Solve it. Do you guys want me to do that, or would you rather me move on to one of the integration problems? If you haven't solved a definite integral, there is. And the issue with it is because like I said, like you can mess up, like for one, you see that both of these terms end up going to 0, right? You can mess up somewhere in here by like forgetting to add something or forgetting to multiply 2 times something. I forgot to multiply 2 and 1 together in one version of this practice, or one version of this problem, and that specifically is what cost me an A for that test specifically. So I remember being so frustrated at myself that I forgot to multiply, like, or distribute the 2 to 2 different things. And it didn't affect my final answer, but it did affect my answer for this term, I want to say. Like my term right here wasn't exactly right. I think it was like off in the numerator or something. So just be really careful and explicit with your parentheses use. You can see that I use a lot of parentheses. So, but yeah, I would encourage you, if you have time, to integrate that. But I'm going to move on to 12.3 because we will get enough definite integral practice. I guess before I move on, would you be interested, for those that are here today, if I extended my SI session by like an hour and did one of these problems, like a different version, like not this exact same problem, but if I like made a different one? Okay. Okay. All right. I will do that then. I will send out an email with the correct. Not today. I'm not going to do another one of this today, but I'll do another like Riemann sum problem, just like 12.2 on like I'll extend my hours to make sure that I've covered everything, and do a different version. Like it'll be like sum x squared plus other things. Because he said on the exam there might be other different terms, so I want to make sure that you guys are prepared for that. All right, let's move on to the integration, the definite integrals. Well, I guess we move on to 12.3 first. 12.3 should just be, you get this problem. It's a free 5 points. If you understand what the fundamental theorem of calculus is, it's a free B problem. So please understand it. And all the problem is asking is, I think it states, given f of x is equal to the integral e to the pi, and it's going to look scary, but you don't have to actually integrate this problem, so don't be scared, right? And it's going to be the sine of the tangent of the natural log of t squared plus 1. I'm going to have to shorten my screen, dx. So given that integral, right, they want you to find f prime of x, right? And if you haven't read the chapter, you probably don't know what the first part, oh, dt, you were right, it's dt, not dx, thank you. So if you haven't read the chapter or watched the videos, I think the videos are out, but if you haven't watched that, you don't know what the fundamental theorem of calculus part 1 is. And all that it states is that f prime of x is going to be equal to the derivative of f of t, and then this is going to be equal to f of x. So all it is saying that like the derivative of an integral is just the function that's on the inside. That's basically what this is saying. So all you have to do is just replace those t's with x's. And does he do that on the practice exam on his answers? I genuinely can't remember. Because the theorem does that, but I wonder if he does that. Yeah, he does do that. All you're going to do is just replace the t's with x's, and then that's your answer, right? Does that make sense? Like the opposite of an antiderivative is a derivative. So your answer is literally just going to be this whole thing, but with x's instead of t's. So f prime of x is simply going to be sine of the tangent of the natural log of x squared plus 1. And that's just the answer. So if you just remember to switch that, and whatever variable, it should be whatever variable is up here is what you replace with a t. So if there's not an x up there, and if it's like a y or something, then replace it with y. Does that make sense? But theoretically, it should just be a give me, if you know that. No, this dt stays up here. This dt stays up here. Because the variable in this integral is t. But whenever you evaluate this and then you take the derivative, it's going to take on that variable right there. Alright, so now we get some actual definite integral practice, which is very similar to what we've been doing with antiderivatives, but at the very end you plug in numbers instead of having that plus c at the end, right? If you're given the numbers to evaluate it at, you don't have a constant, you just you find what the integral is at that point, or over that integral, or over that space is what I meant. Like over the area in the graph, right? So for 12.4, we have the integral from 1 to 4, root x dx. We know whenever we see a root, what do we need to do? Yeah, the exponent. Awesome, guys, yeah. So we're going to change that root to an exponent. X to the 1/2 dx. And then we're going to use our reverse power rule, right? So we're going to add 1 to that exponent. 1 plus 1/2 is going to be 3/2. Divide that 3/2 by 1. And then we have x raised to the 3/2 power. And then we're going to evaluate it from 1 to 4. Right? This is the notation I use. I don't think it's super common. I think most people like just do that line at the ends. I think there are other ways to do it, but to me it just looks so much better when it's wrapped. You know exactly what you're evaluating, so I just do the brackets with the points at the end. So does he care? No. I mean, whenever I took him for Calc 1, 2, or not 2, 2, 3, and ODE, this is how I wrote integrals, and he always accepted it. So doing it this way is fine. I mean, anyone that knows how to integrate will understand what you're doing. So it's a non-issue. And all this numbers at the end means is that for the number up top, your b, you're going to evaluate this whole thing at that, and then you're going to subtract that whole function evaluated at 1. Right? So what this is going to look like is we can resimplify that 2/3. Yeah, so we found the antiderivative, or technically we found just, yeah, we found the antiderivative. If you want to, I guess I'll do this in the next problem. You can rewrite it as an antiderivative without those numbers and solve it that way with the plus c, and then rewrite it and plug in the numbers. I think that's more useful when you get to Calc 2, when you do stuff like U substitution. It's a lot more useful, in my opinion, for various reasons. It's not that big of a deal right now, but once you get to the beginning of Calc 2, it's really useful to rewrite it as an indefinite integral. I guess I'll do that for the next problem because it's good practice. But I just rearranged that, the 1 divided by 3 over 2 to 2/3, and now I'm going to plug in the 4 and the 1. So I'm going to plug in 4, so we have 2/3, and then I'm going to rewrite this as root 4 raised to the 3rd power, right? That's what that 2/3 means. It means a square root with that number raised to the 3rd power, minus, and then whenever I have a minus right there, because you could have multiple terms in here, I always wrap it in parentheses. You wrap the whole function in parentheses because it's really easy if there's multiple terms to not distribute that negative sign, which you have to do. Otherwise, you're going to get the wrong answer. So I would always, always, always wrap that second part in parentheses, even if it's just one term, because it builds good habit. Right, for that square root 4 to the 3rd, we know that 4 squared times 4 is 4 cubed. And this is just going to be 2/3. We know that we can just pull out that 4 since the opposite of a square is the square root. So we're going to have 2/3 times 4 times root 4. We know root 4 is just 2. So 2/3 times 4 times 2 minus 2/3. So 4 times 2 is 8. 8 times 2 is 16 over 3 minus 2 over 3 equals 14 over 3. So that's our final answer for this problem. I need to remember to zoom back in for the next one. Was there any questions? This one should have been, I mean, I don't know how much you guys have tried this, so it might have been difficult if you haven't, especially if you haven't done a ton of these problems. But this should be one of the relatively easier problems. There's some simplifying that we had to do whenever we plugged in the numbers, but the calculus itself shouldn't have been that bad. Any questions? All right. Let's move on to 12.5. All right, so we're going to have the integral from 1 to 3, and then we have x squared minus x minus 10 dx. Right. So I am going to rewrite this as just an indefinite integral. If you're moving on to Calc 2, it's probably good practice to go and start doing that. You can keep it like that, but you'll see when we get to like the more advanced methods of why we sometimes don't do that. Or at least I don't. It's honestly up to personal preference. But just if you are taking Dr. Noring, this is the way that he prefers to do it, so not that the other way's wrong, you can do it the other way. But you're more likely to make mistakes. So we're going to rewrite this as an indefinite integral, which is just rewriting it without the numbers. So what's the first thing that we do when we look at this? What do you think we should do? Should we, I mean, we can do a lot of things. We can integrate it as is, or we can split it up. What do you guys want to do? Split it as is, split it up, split it up. It seems like the consensus is separated, so splitting it up less complicated. I mean, it's about the same. I think if you don't know when to factor out like constants and stuff like that, it's best to just always separate it, because then you don't mess up on stuff like that. So I think like in the terms of making mistakes, if you're new to integration, separating it is better. But once you've done it enough, like personally now at this point, I would keep it as is. But I know for a lot of you that's not the case. Like a lot of you feel like you should still separate it, which is totally fine and valid. Like I encourage you to do that, especially if you're prone to making mistakes like that, you know. And you know yourself better than anyone, so you can determine that for yourself, right? But let's split it up for now. Either way is fine. If you want to keep it as is, that is totally fine. But we are going to split this up to get 3 separate integrals. All we did is put an integral and a dx in front of each in each term, right? And we also brought out those minus signs. All right, so now we're going to use our power rule, right? So what's the antiderivative of that first one going to be? You don't have to include the plus c, we'll just do that at the end. Yeah, it's going to be x cubed divided by 3. You're thinking the opposite way, Samantha. That's the derivative. Yeah, it happens, trust me. I still do that sometimes. But it is going to be x cubed divided by 3. And then what about that second one? Yep, x squared divided by 2. And then what about the last one? Yep, 10x. And then we have that plus c. So once you've solved the indefinite integral, I like to do little bullet points, like this is you can do however way you want, but I do like a bullet point where this is the indefinite integral, and now we're going to do the definite integral. So the definite integral of x squared minus x minus 10 dx is equal to x cubed divided by 3 minus x squared divided by 2 minus 10x, evaluated at 1 and 3. And now we're going to do that same thing. We're going to plug in that 3 And you see we have multiple terms, so we should really be wrapping in parentheses in both times, especially the second time. Right, so we have 3 cubed over 3 minus 3 squared over 2 minus 10 times 3 and 1. So 1 cubed is going to be 1 divided by 3. 1 squared is 1, so 1 divided by 2. 10 times 1 is just going to be 10. So 3 cubed divided by 3 is going to be 3 squared. 3 squared is 9. Minus 9 over 2 minus 30 minus, and you see we're going to distribute this negative sign, right, to each of them, and it's going to change the signs of all of them. So we're going to have minus 1/3 plus 1/2 plus 10. Okay. Yeah, so we have a negative 30, a 9, and a 10. So that's going to be 11, negative 11. Yeah. For some reason, on mine, I just realized I made a mistake with that 30. No, it wouldn't, because 3 cubed, on top we have 3 times 3 times 3, divided by 3, one of the 3's cancel out to get 3 times 3. Yeah. Negative 20 plus 9 is negative 11. Yeah, so adding these terms together, we get negative 11. Oh yeah, you're fine. Yeah, it's easy to make that mistake. And so we have minus 9/2 plus 1/2, so that's going to be a negative 8/2. And then we have that minus 1/3. Right? Negative 8/2 is going to be negative 4. Negative 11 minus 4 is negative 15. Minus 1/3. 15 times 3 over 3, negative 45, divided by 3 minus 1/3. And so that's going to be negative 46 over 3. And that's our final answer. Sorry, I just wanted to double check myself because I made a mistake on this one. Even I make mistakes still. Like, I think when I wrote it down initially, I wrote this one as a plus instead of a minus, which is why I just did the whole problem wrong. No problem, Samantha. Thanks for coming. All right, well, we are out of time. I don't have, it'll take more than 2 minutes to do another one of these, but we will, 4.6 would just be 0. No, 4.6 is not just 0. Bye, Abby, thanks for coming. 4.6, so what did you get when you did the antiderivative? Noah, because we can talk about it. Yeah, no problem. Thanks for coming. Yeah, what's your question for 12?